Welcome back. In the last lecture, we talked about the Hamilton method. And the Hamilton method was a way to determine how many representatives each state should get. So here's one of the examples that we did in the last lecture. So here, we're sharing 83 buses among these three locations, Boston, Chicago, and Sacramento. And we want to share it based on the number of riders. So think of the 83 buses as 83 representatives, these locations as states, and the number of riders as population. And the way the Hamilton method works is the Hamilton method starts off by finding the standard divisor. And we're going to use the standard divisor to divide each of the population by the standard divisor. We get these decimal numbers. In the Hamilton method, you always round down, and then you check the total, right? If the total is the correct number, in this case it was 83, then you're done. If it's not the correct number and you have extras to give, you give the extras based on the decimal part. Right? Whoever has the biggest decimal part will get the extras. And then you have more extras, you give it to the next biggest decimal part. And we saw that with the Hamilton method, we had these three paradoxes, which don't happen often, but they can happen. So these were situations where a state ends up losing their representative in a really unexpected way. And those situations happen in part because we're giving away these extras. So notice how in this example, we gave the extra to 668 and 667. But 665, which is close to 667 and 668, didn't get an extra. So it's so close that if anything changes even a little bit, what could happen is right now 665 is in third place. If you say change the population or add on a new representative or add on a new state, so any small changes could put this third place into first place. And if that happens, then Chicago is going to get the extra, which means either Boston or Sacramento is going to lose their representative. So these paradoxes are happening in part because we're giving away these extras at the end. So Jefferson, to fix this, what Jefferson proposed is to not give these extras in the end. So what he suggests is to modify this divisor. So to pick a different divisor so that when we divide, round down, that we get the exact number that we want. One of the downsides of the Jefferson method, which by the way was proposed by Thomas Jefferson, our third president, same guy that's on the $2 bill. One of the downsides is that we have to guess the modified divisor, this divisor that we're going to be using to divide. Now, if you're lucky, you'll get it in the first couple of tries. If you're unlucky, it may take you 20 tries, 30 tries. So that's one of the downsides of the Jefferson method. For the problems that I give you in this class, you should be able to get it in 2 tries because I'm going to give you the starting one to try, and then based on whether or not that works, that should tell you what the next thing you should try is. And I picked a number so that you should be able to get it in the next try. So in this example, we're talking about the same thing, 83 buses shared among these 3 cities based on a number of riders. And I'm going to start you off with the first modified divisor. So we're going to be using 222 as our first guess. In all the problems, I'm going to give you that first guess. So what we're going to do is we're going to take 222 and divide each of these number of riders by 222. Let me set that up, and then we'll use a calculator at the end. Chicago. Right, so divide each of the number of riders by 222. And round to 3 decimal places. So this is 33.910. Next up, 9540 divided by 222. 42.973. 1491 divided by 222, 6.716. And similar to the Hamilton method, you round down. Which is the same thing as just ignore the decimal part. So this would be 33, 42, 6. And then you're going to check the total. $33 plus 42 plus 6. And we get 81. So the number of buses we have is 83. So this is not the number I want, right? I want this to be 83. It's not. So in the Hamilton method, you give the extras based on the decimal. In the Jefferson method, you don't do that, okay? If you don't get the correct number, what you're going to do is you're going to guess a different number for the divisor. So instead of 2 to 2, we're either going to go up or go down and try it again with the new divisor, right? So right now, 81 is too low or too little. Because we really want 83. So if it's too little, should I increase this to 223 or should I decrease it to 221? So let's think about this. It's too little, so I want these numbers to be bigger, right? I want these numbers to be bigger. So how do I get that bigger? Should I divide by 223 or should I divide by 221? What's going to give me bigger numbers right here? And here's where you have to think back to what you know about division. Dividing by a smaller number should give you a bigger number overall, right? So we want to divide by a smaller number here instead of 222, right? So if I divide by a smaller number, overall, I should get bigger numbers here. So if it's too little, I should go down. And we're going to go down to 221. And then we're going to try it again. All right, so if it's too little, you'll go down. If it's too much, you'll go up. So we're going to try it again with 221. So 7528 over 221. Chicago 9540 over 221. And Sacramento 1491 over 221. Right? Divide. 7528 divided by 221. Round to 3 decimal places. This is 34.063. $9,540 divided by 221. 43.167. 1491 over 221. 6.747. Once again, round down and then check your total. Okay, that's going to be 34, 43, 6. Right, round down, same thing as just chopping off the decimal part. And then check the total. $34 plus 43 plus 6. And we get 83. And this is the number I want, right? I have 83 buses, and I use 83 buses here. If that's the case, you're done. So our final answer is 34, 43, and 6. So for the problems I give you, I'm going to give you the starting guess. That guess is not going to work. And then depending on whether it's too little or too much, you should either go up or down. And if you pick the right direction, your next guess should work. All right, let's try the Jefferson method on another example. In this example, we're talking about 71 delivery drivers that we need to share among these regions, north, south, east, west, based on a number of packages that need to be delivered in those regions. So I'm going to start you off with a first guess of 34. So we're going to use this modified divisor and divide each of these packages number by 34. All right, we'll use a calculator to divide, and then we're going to round down. So 261 divided by 34. Rounded to 3 decimal places, this is 7.676. 514 divided by 34. 15.118. 766 divided by 34. 22.529. 1019 divided by 34. 29.971. Okay, we're going to round down and then check the total. 7 rounded down will be 7. 15.118 rounded down will be 15. 22. 29. And then we'll check the total. So 7 plus 15 plus 22 plus 29. And we get 73. And that's not the right number I want. I only have 71 drivers, and here we're using 73. So we used too much. Now the question is, for our next guess, do we want to go up to 35 or do we want to go down to 33? So right now it's too much, which means I want these numbers to be smaller, right? These numbers to be smaller. So how do I get a smaller number? I get a smaller number by dividing by a bigger number, right? So I want to divide by a bigger number, which means I want to increase the 34 to a 35. So if it's too much, you should go up. So our next guess, I want to be 35. Okay, so either you go through that reasoning, or just remember, if it's too little, go down. If it's too much, go up. Okay, so right now 73 is too much. I only have 71 drivers, which means I need to go up. It was 34, I'm going to go up to 35. And then do the same thing again. Divide each of the packages number by 35. Okay, use the calculator. $7.457. $14.686. $21.886. 1019 over 35. 29.114. Round down, which is the same thing as just ignoring the decimal. So we'll get 7, 14, 21, 29. And then you'll check the total. 7 plus 14 plus 21 plus 29. 71. Is that the number I want? Yes, I have 71 drivers. I did get exactly 71, so that's exactly what I want, which means my final answer is going to be 7, 14, 21, and 29. So for the problems I gave you in this class, if you do it correctly, on that second attempt, it should work out to be exactly the number that you want. Now that we've seen both the Hamilton method and the Jefferson method, let's compare the two. In terms of computation, I would say that the Hamilton method is more straightforward. Mostly because it doesn't involve any guesswork. You start off by finding the standard divisor. You use it to divide each of the populations by. You'll get decimal answers, which you round down. You check the total. If the total is correct, you're done. If you have extras, you give the extras based on the highest decimal part, right? Whoever has the highest decimal part will get the extras. So that's the Hamilton method. The Jefferson method does involve guesswork, so you have to guess the modified divisor. Which can be time consuming. For the questions I give you in this class, you're always going to find the correct modified divisor in 2 tries because I'm giving you that first guess. But if I didn't give you that first guess, if you're lucky, you'll get the correct modified divisor in a couple tries. If you're unlucky, it may take you 10 tries, it may take you 20 tries, it may take you 30 tries. And what's even worse, for the questions I give you, the modified divisor that ends up working is going to be a whole number, right? So you're limiting your guess to whole numbers. But in reality, you might end up having to use decimals there. So not only do you have to guess, but the guess might be decimals, which makes it even more time consuming to figure out which decimal actually works. In terms of the paradoxes, the Alabama, the new state, and the population paradoxes, so those are only issues with the Hamilton method. So in the Hamilton method, the paradoxes could occur. So these were situations where we added a representative, a new state was added, or the population changes. And in those situations, one of the states ends up losing their representative in a really unexpected way. So you can think of these paradoxes as a flaw of the Hamilton method. So these are kind of undesirable properties of the Hamilton method. Now, the Jefferson method, these paradoxes don't occur. So in that sense, the Jefferson method is a little better because the paradoxes aren't an issue. But the Jefferson method has another issue, which is called the quota rule. So before I talk about the differences, let me actually explain what the quota rule is. So before I do that, I have to explain what the standard quota is. So the standard quota is the decimal answer that we get before we round in either the percent method or the Hamilton method. And I'll explain what that is. So here's the Hamilton method with our 83 buses example. And here is the percent method with the same situation, the 83 buses. So the standard quota that I'm talking about are these numbers, these decimal numbers before we round it, or these decimal numbers before we round it. So what these decimal numbers represent is, it represents exactly how many buses each city deserves, right? If we were able to cut up the buses. So if I was able to cut up the bus, Boston deserves exactly 33.698 buses. So it doesn't make sense in a bus situation, but if we're talking about, say, gallons of oil, these numbers do make sense. So Boston deserves exactly 33.698 gallons of oil. And if we're talking about oil, right, you can measure out exactly 0.698 gallons of oil. But because we're talking about buses and we can't cut up, that's why we have to round. So the standard quota are these decimal numbers before we round, and they represent exactly how much each city or state deserves. Now, I know these numbers are different, but they're actually supposed to be the same. And the only reason why they're different is because we rounded. So if we use exact answers, the percent method and the Hamilton method should be exactly the same in terms of those numbers, those decimals before we rounded. So that's the standard quota. Now the quota rule says that the number of representatives each state gets should be within one of the standard quota. And what do I mean by this? Okay, so here's the Hamilton method for those 83 buses. Let's look at Sacramento. So the standard quota, which is the number before we rounded, was 6.668. So that's exactly how many buses Sacramento deserves. So what the quota rule says is that we're okay with 6, given 6 to Sacramento. We're okay with 7 to Sacramento, but we're not okay with 8 to Sacramento. So we're okay with 6. We're okay with bumping it up by 1 to 7, which we did, but we're not okay with another bump to 8. Okay? So what we're saying here is that we don't want states to get 2 bumps. Right? We're okay with 1 bump, but we're not okay with 2 bumps, because if a state gets 2 bumps, then basically they're getting way more representatives than they deserve. Okay, so that's what the quota rule is. And the issue with the Jefferson method is that it sometimes violates the quota rule. It doesn't happen all the time, but sometimes it could happen where the quota rule is violated. Okay, which could be thought of as a flaw of the Jefferson method. So sometimes you end up with a state that gets too many representatives, then more representatives than they deserve. Now, Hamilton method, on the other hand, does not violate the quota rule. So neither method is perfect. All right, for our last example here, what I want to do is answer this question using both the Hamilton method and a Jefferson method, and then compare the 2 answers at the end. So the situation we have is 43 nurses that need to be shared among 3 hospitals, and we want to share it based on the number of beds at each hospital. So the first part here, I want to do it using the Hamilton method. So for the Hamilton method, I need to start by finding the total. So 406 plus 475 plus 649. .406 plus 475 plus 649. And we have a total of 1,530. These are beds. Okay. The first step in the Hamilton method is to calculate the standard divisor. And to find the standard divisor, you're going to take your total that you just found, 1530. And let me label the units on this. So this is 1,530 beds. And then divide it by the thing that we're sharing. So we're sharing 43 nurses among these hospitals. So 43 nurses. Divide 1530 divided by 43. Rounded to 3 decimal places. This is 35.581. I'm going to force this to be a fraction by putting it over 1. And then let me label the units on top and the units on bottom. So up top were the beds. At the bottom, it was the thing that we're sharing, which were the nurses. And the interpretation of the standard divisor is for every 35.581 beds, the hospital deserves 1 nurse. Okay? And what we're going to do is divide each of these number of beds, by this 35.581. Okay? So for hospital A, 406 divided by 35.581. Hospital B, 475 divided by 35.581. Hospital C, 649 divided by 35.581. All right, so on our calculator, 406 divided by 35.581 is 11.411. That's rounded to 3 decimal places. Next up, 475 divided by 35.581. 13.350. And then finally, 649 divided by 35.581. 18.240. Okay, so those are what we called the standard quota on the previous page. And then the Hamilton method, you round down. Which is the same thing as just ignoring the decimal part. So we'll get 11, 13, 18. And then check the total and see if it's the correct number that we want. So 11 plus 13 plus 18 is 42. What number do I want? So what I'm sharing is 43 nurses, so I'm looking for 43. I've only used 42 so far, which means I have 1 extra. Who gets the extra? So if you have extras, you're going to give the extra based on the decimal part. So whoever has the highest decimal part will get the extra. 411 versus 350 versus 240, which means the 411 is going to get it. So hospital A is going to get an extra, and they'll be at 12. And we only had 1 extra to give, so this will be 13, and this will stay 18. And that's the Hamilton method. So now we'll do the apportionment, this time using the Jefferson method. So with the Jefferson method, I'm going to give you the first guess. So this is the number that we're going to divide each of these numbers by. Okay. So the number of beds in hospital A was 406, divided by 35. Hospital B is 475, divided by 35. And hospital C is 649, divided by 35. Right, on our calculator, 406 divided by 35. 11.6. We're rounded to 3 decimal places, so if you end up with a number that doesn't have a long decimal, just add on zeros until you get 3. B, 475, divided by 35. 13.571. 649 divided by 35. 18.543. Right, Jefferson method, you round down. Which basically means ignore the decimal. And this will be 11, 13, 18. And then you're going to check the total. 11 plus 13 plus 18 is 42. If that's the correct number you want, then you're done. If not, then you have to continue. Is that the correct number? We had 43 nurses, so I'm looking for 43 as my answer. So 42 is not the correct answer. So unlike the Hamilton method, we don't give extras with the Jefferson method. So if you don't get the number you want, you're going to go and guess again and change this divisor to something else, right? So right now, we have 42, which is too little, right? We wanted 43. So this is too little. And do you remember, if it's too little, do you go up or do you go down? If it's too little, we wanted these numbers to be bigger. To get a bigger number here as a overall, you want to divide by a smaller number. So we actually want to go down. So too little, go down. If it's too much, go up. So the next guess we want to try is we want to go down from 35, which means we want to try 34. And then do the same thing, divide. 406 divided by 34. 475 divided by 34. And 649 divided by 34. Right, so each of the same numbers, this time divided by 34. Okay, 406 divided by 34 is 11.941. 475 divided by 34, 13.971. And then finally 649 divided by 34, 19.088. Round down. That's going to be 11, 13, 19. Right? Basically, just ignore the decimal part. And then check your total again. Most likely, if you went the right direction, right, went up or down, if you chose the right direction, the second attempt should give you what you want. So 11 plus 13 plus 19 is 43. Which is exactly what I wanted. So that's the number of nurses that I have, and I used them all. So our final answer is 11, 13, 19. And then part C, I'm asking you to compare the two apportionments. So with the Hamilton method, we had A got 12, B got 13, and C got 18. With the Jefferson method, A got 11, B got 13, and C got 19. And the question I asked you is which hospital would prefer the Hamilton method and which hospital would prefer the Jefferson method. So let's go with A. Okay, so A, which method would A prefer? So A got 12 nurses with the Hamilton method and 11 nurses with the Jefferson method. So probably A is going to prefer the Hamilton method, which will give it more nurses, right? So A probably prefers the Hamilton method. What about B? So B got 13 with Hamilton and 13 with Jefferson. B probably doesn't care. Because they're getting the same with both methods. What about C? C got 18 with Hamilton and 19 with Jefferson. So C probably wants Jefferson. So C prefers Jefferson. Because they'll get more nurses with the Jefferson method. And then the last question I asked here is which apportionment would you choose? So the takeaway I want you to take away from these past two lectures is that Hamilton versus Jefferson, which one is better? It's a matter of opinion, right? So they both have flaws, and in fact, any apportionment method is going to have flaws. And really, there is no best method. So you may be used to math having one correct answer, but this is a situation where there's no correct or no best answer. The best answer depends on who you talk to, right? C, if you ask C, C is going to say Jefferson is the best. If you ask A is going to say Hamilton is the best. And which method actually is used most of the time depends on who's in power, right? Whoever's in power is going to choose the method that benefits them the most. So that's what I want you to take away from these past couple lectures. All right, so that's all I have for you today. Have a great day, and I'll see you in the next one.